Right, I've started the recording. So good afternoon, everyone. Thank you very much for joining the 6th UKTC online talks series. So today we are going to have 4 talks as usual, and the focus will be on, it's a quite broad theme, but it's about fundamentals of turbulence. So we are going to have the first speaker from Imperial College from the Department of Aeronautics, Hanxun Yao, who is working with George Papadakis. And the talk is about interscale energy transfer in the boundary layer undergoing bypass transition. So Hanxun, the stage is yours. And if you can try to stick to 15 minutes, that would be amazing. Thank you.
Okay, thank you for the introduction and welcome to my talk. I'm Hanxun Yao, a PhD student from Imperial College. And today I'm going to be presenting part of my PhD work. And this has been supervised by George Papadakis. And also I'd like to thank Dr. Jempa Molicum from Chalmers for many discussions and help on this work. So in this work, we're interested in interscale energy transfer of boundary layer bypass transition. So what's bypass transition? Bypass transition is a laminar to turbulent transition process within boundary layer. And in this case, the linear TS wave is bypassed. That's why it is called bypass transition. There are several ways to track transition, for example, the roughness on the wall. And in our case, we focus on the bypass transition due to a high intensity free stream turbulence. The picture here shows our computational domain, and the contour here is the streamwise velocity fluctuations at a fixed wall normal location. We can see these high and low speed streaks before transition, and these streaks are also called of modes. Streaks break down to the turbulent spot, and growth and propagating finally merge with the turbulent region. So this is the general picture of bypass transition, and this happens very often in turbulent machinery. And here we show some validation cases of our database. So the skin friction coefficient is compared with the T3A experimental data. We have also calculated the TKA budget at the fully turbulent region compared with last DNS data. All showed very good agreements. And our DNS database has 351 snapshots of the flow field. And for more details of our DNA simulation in terms of the numerical scheme and index condition, please find the paper we published last year. So what's the motivation of this work? And as we can see from the flow field, during the transition, the flows have a wide range of scales, such as this loam structure in the laminar region and turbulent spots and the structures inside the fully turbulent region. So we're interested in how the energy transfers between these scales and trying to figure out if there's any forward or inverse cascade process. In order to describe the energy transfer between scales, let's first have a look at what property we're using to represent energy at different length scale. What we'll be introducing here is the second order structure function, which is the squaring of the velocity difference between 2 points. And here plus and minus means 2 points in the physical domain. The physical meaning of the structure function is the energy within an eddy of length scale r. This also regarded as scale energy in some papers. And this is the description for homogeneous and isentropic turbulence. In this case, eddies are independent its location and its orientation. For the homogeneous and anisentropic turbulence, the eddy is independent to its location, not for the separations. Sorry, not for the orientation. So in this case, we have to add the separation between the 2 points as a variable to represent its orientation. The more general case, which is the inhomogeneous and anisentropic turbulence, the eddy rely on both separation between the 2 points and also its location. And the location here is represented by the middle points of the middle points of the coordinates of the 2 points. So it has 6 dimensions in total. And this is the case we're interested in. So what's the dynamics of this structure function? And what's the governing equation of the structure function? In 2002, he developed generalized Kolmogorov equation. And this equation is the transport equation of the structure function. It is derived directly from the Navier-Stokes equation. And here we have used the Reynolds decomposition to account for the mean flow. So this equation has no any assumption, is theoretically used for any kinds of incompressible flow. And each of this term has physical meaning. For example, the first term, which is the transient term, it is 0 because here we consider only the statistically steady flow. The second term is the advection due to mean flow, and that's nonlinear interscale energy transfer rates, and that's interscale energy transfer between due to mean flow, turbulent advection, pressure velocity correlation, diffusion in physical and scale space, and the last 2 terms are the production and the dissipation. Capital X here is the middle point's coordinates, and that represents physical space. As small r here is the separation representing scale space. These are corresponding to the 6 dimensions I mentioned in the previous slides. And this equation looks quite complicated, but for homogeneous and isentropic flows, we can discard the derivative of capital X and all this term with capital U, which is the main flow. So this equation can recover the classic Kolmogorov equation. It will further consider only the scales at the inertial range. And this equation deduces the famous Kolmogorov equilibrium. In order to use this very complicated equation in the more physical sense, we can rewrite it into a divergence form. Energy flux vector then can be in physical space can be then concluded as phi s, and energy flux vector in scale space can be concluded as phi r. We have also left the production minus the dissipation at the net production term. Physical meaning of this flux can be explained by integrating, for example, the divergence of the flux, scale flux over a volume with radius r. Using Gauss divergence theorem, this can end up with a surface integration. So if the production between the energy flux vector and unit normal vector at the surface is negative, that means energy is transferred inwards and representing a local forward cascade. If the production is positive, energy is transferred outwards, and that representing a local inverse cascade. And this is how we apply this equation to our bypass transition case. In the physical space, time and spanwise averaging are implemented, and the world normal direction capital Y is a variable. We have also fixed the streamwise locations at 5 different streamwise locations here. LA means laminar, one location at laminar region. TR is at transitional region, and TU is at fully turbulent region. And in this presentation, because of the time restriction, I only show the results at LA TR1, which is at the early stage of transition, and TU. The scale space, we consider only R1 and R3, which are the separation in streamwise and spanwise direction. Wall normal direction separation is said to be 0. And by doing this simplification, we can project the flux vector and each term of this equation into a 3-dimensional hyperplane. And this is where we're going to present our results. We first show here is the net production term in the 3D domain. The isosurface here is defined by the maximum value of the net production multiplied by 0.7. We can see this production peak in 3 different streamwise locations are all located at a specific spanwise length scale. We found this length scale is determined by the average spacing in the low and high speed streaks. And the peak in the low direction is determined by the off-diagonal structure function and the shear. This term looks quite similar to the single point TK equation, and indeed we found the height of this peak in the fully turbulent region is around the layer, and of course in all units. So we conclude that physical meaning of the production peak tells that the mean flow injects energy at a specific spanwise length scale and one normal distance. We then show the production and also superimposed with the energy flux vector on this domain. We found the similarity of this plot in 3 different locations is that energy originated from net production peak and bends towards 2 dissipation region. One is the wall normal axis, and that's corresponding to a small scale zone, and another one bending towards the wall. This is similar to what we found in channel flow. But what we found more interesting here is during the transition, there's a strong positive flux, as shown at this red arrows. And this is telling us there is a strong inverse cascade is taking place. And we are going to pay more attention on this region. This strong positive flux can even found in a very large domain. So we're trying to figure out what exactly determines the inverse cascade. So we then compose the energy flux vector in the physical space and scale space to 4 pairs. They are due to the mean flows, the fluctuations, pressure, and this is due to the viscous diffusion. Denoted by the superscripts and capital M, F, V, and P. And this decomposed energy flux is projected on a 2-dimensional plane. And this is done by selecting a section from the 3D domain. And also this plane is right across the net production peak. On the top and bottom panels are the decompositions from the middle one, where we show the total flux. And here we only show the mean flow contribution and the fluctuation contribution because they're the dominant ones. However, the viscous diffusion and pressure are relatively small. It's obvious to see that the large positive flux from the production peak is due to turbulent fluctuation. Mean flow, on the other hand, contributes to the opposite side. So we conclude that there's a computation between the flux due to mean flow inhomogeneity, which is the mean flux, and the nonlinear interaction. And in this case, the later one, which is the flux due to turbulent fluctuation, is the dominant. It is also interesting to see if the positive flux is linked to the instantaneous flow field. We're intuitively thinking it might due to the intermittent turbulence spots. So we picked a time series of the flow field at a specific height where the inverse cascade is taking place. The contour here is the wall normal fluctuation, from which we can see the formation of one turbulent spot, like this. We then use the third instance to do some instantaneous analysis within this yellow rectangle. And here's the result. Remember that the turbulent fluctuation flux is determined by the velocity difference between 2 points, which are denoted by plus and minor. In this instantaneous calculation, we fix the middle point here, and any other points within this domain will be the plus points corresponding to here. And the minor points is on the other hand, on the other side, which is not showing here. We can then calculate the instantaneous flux vector as shown as these red rows. The contour on the top is the one normal velocity fluctuation, and the bottom one is the streamwise velocity fluctuations. You can clearly see that fluxes have very strong correlation with the streamwise fluctuation. This is telling us that a large positive flux appears whenever the turbulent patches are formed, and especially the plus points are within the spots, and the minor points are outside the points in the upstream terminal region. This case will cause the sign of the dominant flux positive because the instantaneous velocity difference is positive, and that will contribute to instantaneous local inverse cascades. So from this picture, we can see how the strong positive flux is correlated to the growth of the turbulent spots. And here's the conclusion. We have been introducing the generalized Kolmogorov equation as a powerful statistical tool to analyze the interscale energy transfer for homogeneous flows. And in our bypass transition case, particularly, we found there's a strong inverse cascade during the transition that is due to the nonlinear interactions. And this strong inverse cascade is also linked to the growth of the highly intermittent turbulent patches that's formed during the transition. And finally, I would love to thank UKTC for providing additional time of Archer. That's where we're running our DNS simulation. And also, I would love to thank my department and CSC for funding this project. Thank you very much for your attention. If there's any question, thanks.
Thank you very much.
Yeah,
it was a very nice presentation. As before, it might be best if you put your questions on the chat, so everyone can read and see them properly.
Yeah.
But of course, if you want to, we have a couple of minutes. Well, I'm going to start because I have a question. So. The inverse cascade is energy at the small scale going to the large scale. So is it related to the small spots of turbulence that are merging together and something like this?
So yeah, in this case, we so as I showing here, so we showed only the results at the early stage of the transition, and the way we explain the inverse cascades is actually we're saying this streaks of the small turbulent structure is created during the transition by the main flow, and also stretching out in the streamwise direction. So yeah, this inverse cascade is actually linked to this elongated structure in this direction. So that's at very early stage of the transition.
Okay.
Yeah. So yeah, that's why we link the inverse cascades to this instantaneous flow field. So we're saying that is correlated to this small structure that is appear during the transition.
Great, thank you very much. If there's more questions, please feel free to use the chat. And yeah, may I ask the speakers to look at the chat in case there's a questions popping up?
How can
I think if you go at the bottom, there will be there should be a chat symbol for you to look at.
Should I stop sharing first? Or?
Stop sharing your screen. That would be amazing.
Oh, yeah.
So we can move on to Ahmed presentation. If Ahmed can share your screen. Great. We can see your screen. Can you speak?
Yes, yeah. Can you
hear
see
you.
me and can you hear me all right?
Yeah, that's perfect. Thank you very much.
Okay.
So our next speaker is from Cranfield and is supervised by Mark Savage, and it's Ahmed. He's going to talk about reproducible instantaneous structure and turbulent boundary layers with opportunities for control. So please, Ahmed, you have 15 minutes.
Okay, thank you very much for the introduction. And yeah, so I'm Ahmed, and today I'll be talking a bit about the work we've been doing on reproducible structures and turbulent boundary layers. So I'll go through a quick introduction and then on quickly, hopefully, to the three main themes, which are the instability development and how we assess the reproducibility of structures, and then some ideas about turbulent spot control that we've tried out. So the main incentive behind the work is flow control for drag reduction, which is basically a very active area by the main manufacturers, and also for business jets and other applications where skin friction tends to dominate the drag profile. And basically, there are many ideas about how to go about taking advantage of that difference in the drag levels. And one of the interesting ideas that have been developed recently is that seeing that transitional flow tends to start off with relatively simple flows, and even the initial stages of instability development, say certainly with the linear part of it at least, tends to be very reproducible and predictable, then there must be a point, and usually towards the later stages of the transition process, where that reproducibility and predictability is lost. And the question of interest was whether it's possible to influence that point, or whether it can potentially be pushed a bit downstream, so that there's a region of overlap between reproducibility and turbulent flow. And some of the experimental evidence from Kachanov and Burudlin, and also by Gaster, and more recently by Wang and Shua, seems to suggest that that might be the case under certain construction of forcing terms that tend to dominate the disturbance environment. So if that is the case, then there might be an opportunity actually to start and to look at a new approach to control, where we're looking more towards the latter stages of the transition process, which might pose a question with regards to how much of an ability there is to sort of backtrack with the flow. But in a way, it's also a more general approach, because the different routes to transition tend to all have that process in common, which is basically the turbulence, the appearance of spots and their growth, and then interaction to form fully turbulent flow. So previous control work usually tends to focus either on fully developed turbulent flow, or the elimination of disturbances, or maybe dampen the eigenmodes, whereas targeting these turbulent spots might be a more general approach, although it is a bit of a question as well. There is a bit of a question mark as to how much can be achieved at that stage. So this project is in collaboration with the experimental part, which is who worked at Nottingham and City, so with Professor Kinzo Shua and Michael Gaster, Professor Michael Gaster at City. So they've also used the Gaster wind tunnel for low background noise transition experiments, and we were doing the computational part of the work. And our main objectives overall are to generate a data set for the initial development of instabilities in boundary layers, and try to look at how we can potentially look at assessing their reproducibility from a computational perspective, looking and developing some control strategies for these latter parts of the transition, and also investigating the implications perhaps for turbulence and transition modeling. So the code used is Senga 2, which was developed by Stuart Kent at Cambridge. So it's basically a structured finite difference high order solver. Spatial scheme is 10th order explicit centered, and temporal scheme is a low storage Roncata. So the main favorable features are basically having, well, not having to reduce the order at internal boundaries. So you have overlaps between blocks to continue using the same stencil all through. And also the fact that it doesn't include a matrix inversion process. So that also helps speed the code on larger cases. So as a quick sort of illustration of the high order benefit of the code, it's so with a Taylor green, even with 144 cubed relative to the reference, which is a spectral code on 512 cubed, its performance is relatively good. So that's one thing. So with regards to the experiments we're doing here, the general setup is for a a flat plate boundary layer with the inflow is a Lausius laminar boundary layer, and a bit downstream of the inflow we have a forcing term, and the outflow is a characteristic non-reflective boundary condition. The free stream is basically assumed to lie in the top boundary condition. The top boundary of the domain is assumed to lie in the free stream, where the velocity component, v velocity, is assumed to be the Blasius one, and then the u velocity is worked out from the assuming non-rotational flow, so zero z vorticity component. So that gives you the u component. And we're looking at two main cases, one with a single point force in the center of the domain, and then an array of forces across the span. So a bit more about the experimental setup is available on the on this paper, which was published last month, I think, as well. So in a sense, there's a bit more information there. We tend to, yeah. So initially we've done some validation on the initial stages of instability growth. So that's the linear region with the parameters shown here. For the f here is the non-dimensional frequency number. So that was just to verify that we don't get any interaction with the outflow domain, and we're getting what we expect from linear stability theory generally for the point source with a 2D case, and here we have a 3D case for both the streamwise unsteady disturbance component, and we have the normal and the spanwise components. And a similar situation for, so this is a multi-source span case where, again, we're looking mainly at the linear region in this case. Okay, so for the reproducible simulations or reproducibility test simulations where we want to develop into turbulence, what we're using is the a TS frequency sinusoid. So that's the TS, so that's the frequency predicted by linear stability theory to lie in the most unstable, at the highest instability frequency level for the boundary layer. And then we add a white noise component, which is about 15% of amplitude relative to the TS wave. And the idea here is to have some sort of controlled uncertainty in the simulation that we can vary later on. So that's very much in line with the experimental setup in this situation. And we've tried to do some TS intensity matching with the experiments to try and ensure that we're getting the sort of flow development within the computational domain. So within the dimensions that are expected of the experiment. It's a bit, so although we have the ratio in terms of amplitudes similar to the experimental noise to or signal to noise ratio as fed by the forcing signal to the speakers they use, but the actual noise spectrum might be a bit different between the two. So we have a cutoff at 2 kilohertz, and that's roughly what they expect as well. So it should be reasonably similar, but obviously not entirely. But with regards to the multi-source experiment, so we've actually allowed it to run and develop structures. So the difficulty with this, with the multi-source case, is that it's a bit difficult to actually isolate a turbulent spot. So what we tend to have is spots developing randomly in the domain. Obviously, with the periodic boundary conditions on the sides, this is basically an infinite domain with forcing terms here, and each of them is fed the same TS wave, but with different noise components. And what we tend to get is the structures we expect to develop. So we can see some lambda structures here going into a turbulent boundary layer. But then the main difficulties is, again, isolating these structures, because the developing spots adjacent to each other tend to interact quickly, and then it's actually difficult to isolate a single one of them. But turning from here onwards to the more interesting, perhaps slightly, case of a single spot developing. So we're looking here at a single, so a case of a single forcing point source at the center of the domain. And we're looking across along the domain in the center line around at half the boundary, near to the wall, but around the region where we expect the large structures to appear. We're seeing the skin friction at the wall, the unsteady velocity components for the streamwise, normal, and spanwise components. And we can see the main, so the linear regime developing, and slightly bigger structures starting to appear that will develop further and then lead to the sort of burst that we can expect with the appearance of a turbulent spot. And what that actually looks like in terms of cuts through the domain is the development of a spot with the expected characteristics, where we have the higher momentum region near the wall, slightly lower momentum region a bit further up. And cut through the near wall region, we can see the expected calmed region towards the end of the spot trailing, with two wing regions defining the half angle of the spot. The higher intensity region near the center, and then over across, looking in the YZ plane, we can see all slight small overhang regions from the sides. So generally speaking, qualitatively, we have the expected spot structure, and also we're looking at instantaneous and span average skin friction profiles across the spot. We can see also that the high intensity turbulent region in the center, at the center of the spot, is where we see that the skin friction hits the turbulent levels first. So, and finally, yeah, with the angle, we also see that the half angle lies within the experimental spread. So that's a bit of an extra. And I think we have, yeah, so here we have one animated with its development through the domain. Obviously, the domain is actually wider on the side, so it goes to -50 and 50, but this one's just looking at, so at the central developing spot, where we get the clean turbulent spot developing through the domain. Okay, so looking at how to assess the reproducibility. So in experimental work, most of the time, or all of the experimental work on this is usually based around the coherence coefficient, which is a statistical measure based on repeat readings. So taking, doing an experiment with measurements until we reach statistical convergence for the RMS values, and then repeating that experiment between 30 and 50 times, and basically comparing the different repetitions with different noise profiles and assessing whether the statistics done on that collective record as a single long experiment is the same as the one which is ensemble averaged of the separate experiments. So obviously, computationally, that would be extensively, will be too expensive. So in a way, we need something that's more affordable. So one approach is to look at the breakdown of symmetry in cases where it exists. So Sandham and Kleiser applied that for channel flow. And the idea here, especially with the single force in term case, where that leads itself relatively well to symmetry, we can try to monitor that breakdown. Now that is also, so that approach is computationally efficient. However, the one thing is that it detects the point at which the flow actually breaks down into a turbulent structures, not necessarily given a sort of overlap region between the region where the flow would show turbulent statistics, but would still be reproducible according to Kachanov's idea. And so in a way, what we wanted to think about is a way of augmenting the asymmetry tracking. So we track the symmetry breakdown, and then at the point of breakdown, try to look at the unsteady velocity ratio and the disturbance, the disturbance velocity ratio relative to the base flow, and try to see whether that can give us some sort of indication about the likely distribution of structures that will remain reproducible or predictable further downstream. So in a sense, what this does is that it gives us a more, so the combination of the symmetry breakdown and this unsteadiness ratio, or there are other ideas such as the length scales available and their expected lifetime as they travel downstream. So in a way, what we're trying to do is to see some sort of metric that's grounded more in the flow physics rather than just the statistics, so that in a sense, it can give us a viable prediction with fewer cases. So with this one, maybe we would look at 2 or 3 of the simulations with different noise profiles. And then that would hopefully give us confirmation that we're lying within the envelope predicted by the combined reproducibility metric here. So that's the general plan. And we're basically still assessing, so we're assessing this one as well as some other ideas with regards to the metric that we're using. As for the approach, so the idea is mainly centered around opposition control, but applied to a stage where the turbulent spot starts taking shape, so that it's in a more generally applicable form for different transition routes. So that was the initial idea. And there were 2 main ways in which we tried to do this. One was with slot jet, so normal slot jet directly under the high momentum region of the flow. And the idea is that this can then be used to lift the high momentum region away from the wall, and maybe also try to target the low momentum region of the spot. The other one was actually using a sort of distributed array of jets in a lambda structure that was also designed to try and target the low momentum region above the a bit away from the wall. And the actual results from that are a bit mixed, in the sense that in the direct vicinity of the jet, so just downstream of it, there is a slight calming of the flow. So there is a bit of a benefit just by the fact that it's lifting the spot a bit up. However, on the sides, what we get is a bit of an increased increased intensity region, partly because of the micro shear layers from the sides of the jet developing, and also just because sometimes it's extruding beyond. So we've tried beyond the spot. So we've tried to test different jet widths across the spot. And also with the lambda structure, it's a similar sort of situation. So it depends. The benefit generally depends on how much we look into. So it's inconclusive, let's say, for the time being, because it depends on how much you look across the span and then how long you allow the spot to develop. And whether or not we have enough of that domain to allow it to develop, so to reach a similar state to its development without control at all, so as to have a reasonable reference, is also a bit of a problem, because it's not only about extending the domain in this streamwise direction, but also we'll probably need to extend it in this panwise direction to limit its interaction with developing instabilities from the sides as well. So in a sense, it's still slightly ongoing work in terms of assessing different methods. And we've also tried looking at more targeting the developing unsteady large structures a bit earlier on in their development region, which in a way does lose a bit of the generality of the approach of targeting the turbulent spots. But it can also be of interesting to see how that so the influence of that on the further development of the flow as compared with allowing it to develop further and targeting it a bit later. So yeah, so in summary, what I hope I've shown is some of the considerations that we've been looking at for the assessment of the reproducibility of the flow and the interaction between control jets and the turbulent spots. And we've also generated quite a large data set of data where we still have terabytes of data basically to go through for things that take a bit more time in terms of the post-processing, such as conditional averaging and other bits of work on turbulent spots that we're hoping to do still. So yeah, so it's very interesting. It's not completely done yet, so we might be back again. I don't know. We'll see how it goes. But it's yeah. So this is where we're at now. And thank you very much.
Thank you very much, Ahmed, for your presentation. Very interesting, and of course, good luck for your ongoing investigations. I think in the interest of time, please ask your questions to Ahmed on the chat. I have some questions. I will use the chat, and thank you again. And may I ask Vishnu, the next speaker, to share his screen?
Can you see?
We can see your screen and we can hear you very well.
Yeah.
Great. So the third talk today is back at Imperial College, and the talk is about the effect of gravity on droplet clustering and decaying turbulence, and this is work done in the Department of Civil and Environmental Engineering under the supervision of Martin. So please, Vishnu, you have 15 minutes.
Thanks, Ruben. Good afternoon, everyone. So this is work done as part of my PhD project. So I'll be looking at the effect of gravity. So what effect sedimenting droplets have on this phenomenon called as droplet clustering of preferential concentration. So I'll just start by briefly introducing the process of preferential concentration. So in turbulent flows, so inertial particles have been observed to accumulate in regions of low vorticity and high strain rate. And one of the mechanisms which causes these particles to accumulate is that vortex cores tend to centrifuge these particles away. And these particles then in turn tend to accumulate in regions of high strain rate and low vorticity. So these have been are usually seen in gas particle-laden flows where the density of the particle is much heavier, is much higher than that of the background carrier flow. So just to see how this preferential concentration happens, so I've taken two simple vortex flows, 2D vortex. So this is a converging flow which is characterized by high strain rate and low vorticity, and a particle and an inertial particle that enters this flow tends to cross these fluid streamlines. So this means that because of the particle inertia, they don't tend to follow the instantaneous flow streamline. Similarly here, so the particle which is moving around a 2D vortex does not necessarily follow the flow, and it tends to be spiral away from the vortex. Now looking at a more complex 3D turbulent flow shown here. So what you see here is the particle positions, which is superimposed on the vorticity field, which you can see in the grayscale. So on the left is much lighter particles. So characterized by the Stokes number, which are closer, which is around 0.1. So these appear more uniformly distributed. But on the other hand, when you look at heavier particles, which are Stokes number closer to 1, you can clearly see particles clustering together in regions of low vorticity. So this has been observed in a wide range of flows. So my work here is mainly focused on the effect of particle clustering inside clouds. So this is an important process because in clouds, clustering can lead to enhanced collision of water droplets. Because of clustering, droplets come closer together, which means that they're more likely to collide. This is in turn is important because this can help explain the fast broadening of cloud droplet size distributions, which is kind of thought as to be one of the possible reasons for why we observe warm rain formation in about half an hour. So if you don't consider the turbulence effects or the clustering, simulations tend to kind of simulate warm rain formation in around closer to an hour. But actual observations show that it's much likely to be closer to half an hour. So in this particular talk, so I'll be focusing on the effect of gravity. So most of the simulations and most of the studies have been conducted with non-sedimenting particles. So we are looking at what effect gravity has on the preferential concentration. And this is important because it breaks the spherical symmetry in the particle pair concentration and also in terms of relative velocity. Because heavier particles, particles of different sizes tend to settle with different velocities when gravity, when you consider the effect of gravity. So just to explain how turbulence affects the collision rates and looking at a couple of relations. So the average geometric collision rate per unit volume is given by this relation. Here, gamma is defined as the average dynamic collision kernel, and N1 and N2 are the number concentrations of the two size groups of the droplets we are considering. So the effect of turbulence manifests itself inside the definition of the dynamic collision kernel. So that happens in two ways. So one is through the radial relative velocity, which quantifies the turbulence effects of the turbulent fluctuations of the carrier fluid. The second is through the radial distribution function, which quantifies the preferential concentration or the cluster. So I'll explain how we define, how we calculate this radial distribution function in DNS. So the simplest definition of the RDF is that it is the ratio of the actual pair concentration to that in a uniform spectrum. So if a particle is uniformly distributed in a flow, you would get an RDF of 1. And if you have clustering, we have regions with very high concentration, the RDF can go up to values of 100 for very small separation distance, which again shows why it's important to consider it in collision. So this is the relation for the RDF, and what we do in DNS is, so if we are looking at the RDF between droplets of size 1 and 2, so we count the number of pairs of droplets of size 2 inside a spherical shell, which is at a distance r and is centered at a droplet of size 1. So you calculate all the number of droplets of size 2 inside the spherical shell divided with the volume of the shell, and then the ratio of that with the particle concentration inside the domain. So N1 and N2 are the total number of particles inside this domain of size W. That gives you the RDF. So we do DNS. So we have developed this new case setup where we try and simulate. So the numerical simulations closely resemble the flow in the test section of the wind tunnel experiments. So the purpose was that there are lots of wind tunnel experiments, but most of the comparisons between the experiments and the numerical simulations are done with very different simulation setups. So we wanted to try develop a setup which would make this comparisons much better. So the grid generated turbulence decays as it moves downstream along the tunnel. So because it is very difficult to numerically simulate an active grid, what we do is we consider a fluid section which is exiting the active grid. And we follow the temporal evolution of this grid as it moves along, moves downstream of the grid. So this is done in the first step. We consider an initial velocity distribution shown here in A. So here so this is the velocity of a fluid section that is exiting a grid. So it has velocity 0 at the grid points, and we give it a velocity UG everywhere. And then we apply Galilean transform to get the initial velocity distribution in the reference frame that we use in the numerical simulation. This is shown here. Then we see random noise, and we perturb the flow and let it develop into isotropic homogeneous turbulence. So this is what we see here. This is the velocity distribution at different time, and this corresponds to different downstream locations in the wind tunnel where the measurements are taken. So initially you see this large effects at the grid, and around 0.4 to 0.5 seconds, the initial conditions, the initial seeding is forgotten, the effects at the grid is forgotten, and that is when we see particles in our domain. So this is a brief animation. So this is a 2D slice. So around 0.4 seconds is when we start seeding particles here. So we use the DNS code Sparkle, and this is a grid size, and we seed 62 million particles in this domain at around 0.4 seconds. And this corresponds to a particle volume fraction of 5 times 10 to the power minus 5. And the 62 million particles includes 36 different radius categories between 20 and 55 microns. So this is similar to the size distribution inside actual clouds. So the governing equations include the continuity equation, the Navier-Stokes, and the droplet dynamics are, so the particle velocities are governed by the Maxey-Riley equations. Here, tau p is a particle relaxation time, which is the characteristic time scale of a particle to react to changes in the background flow. And we consider the effect of gravity as well. So these, in this slide, so we look at the RDF, which is for the radial distribution function between droplets of the same size for non-sedimenting and for sedimenting droplets. So we see a very high levels of RDF up to almost a factor of 10 at scales where the interparticle separation distance normalized by the Kolmogorov scale is less than 1. So this suggests that the mechanism behind particle clustering is not just a simple ejection of particles by vortex force, because we see it at sub-Kolmogorov scales as well. So there are various theoretical studies which looked at the possible reasons, and what they've seen is that there's a power law, an inverse power law relation at scales much less than Kolmogorov scale. And the mechanism behind this is it is a balance between the clustering occurs due to a balance between an inward drift velocity that particles experience due to the inertia and due to the turbulence diffusion. So comparing non-sedimenting and sedimenting droplets, we see that so we characterize the effect of gravity through this non-dimensional number, where it is the settling velocity over the Kolmogorov velocity. So when this non-dimensional number is around a factor of 2, that is when we see the effect of gravity coming into force, and the main effect is that it suppresses clustering. And also, for both cases, there's a maximum when the Stokes numbers are around 0.4, but then the effect of due to the gravity, the magnitude of the maximum is much smaller in the sediment case. So now we look at bidispersed RDS. So that's for the RDF for particles of different sizes. So here there's an additional effect, an additional drift velocity, diffusion velocity due to the difference in the response time for the droplets to the background turbulence acceleration. And the effect of this additional term is to it homogenizes the particle concentration, which results in a much smaller RDF. And then, so you can use this relation to predict the RDFs. So here there's an additional term called RC. So what we see for bidispersed RDFs is that there is a power law relation at much larger scale, and it transitions into a plateau. And the scale at which this plateau happens is this term RC, shown here for the dotted lines. And the effect of gravity is that this transition, where the power law changes to a plateau, it happens at much larger scales. Also, there's a symmetry here. So what we do here is we have fixed one Stokes number at 0.11, and we change Stokes number of the second droplet around these sizes. So this figure is for the top panel is for when the Stokes number of the second droplet is less than the first one, and this is when the Stokes numbers are heavier. So when the particles are heavier than the of size 2 are heavier than size 1. So here we look at is there are a few relations which have been proposed. These are empirical relations, semi-empirical relations for the crossover scale at which this transition happens. So we check this for the relation for non-sedimenting particles in A and sedimenting particles in B. We get very good relation. One very good agreement. One of the good things about getting this good agreement is that because we have a wealth of DNS data at different times for so many particles at so many Stokes numbers, so we can develop empirical ratios for relations for this RC, and along with relations for C0 and C1, which means that we can develop empirical relations for the RDF. So that's something which I'm doing right now. So now looking at the effect on the geometric collision kernels. So here we see the collision kernel, gamma, for non-sedimenting in the top panel and sedimenting droplets in the bottom panel. And B and C are the constituents which makes the constant properties which make up this geometric collision. So this is the RDF, B is the RDF, and C is the relative velocities. So on the right here, so it's just one slice taken from these contour plots because it's easier to interpret here. So the main take-home message is that sedimenting droplets tend to reduce the collision rates for same-size droplets. This is due to a corresponding reduction in the RDF, also in the particle relative velocity. So two droplets which are very close together and which are about to collide. So the effect of gravity means that these the gravity takes over, and then they tend to move along at similar speeds. So this means that there's a lower relative velocity, which means that there's a lower chance of them colliding. However, for particles of unequal sizes, the effect of gravity is to increase the collision kernel. So this is because gravity tends to reduce the RDF for unequal sized droplets, but then there's a much higher increase in the relative velocity. Because particles of different sizes tend to settle at different velocities, which means that they're more likely to collide together. So to conclude, so we looked at the process of preferential concentration in the context of clouds and how they affect the collision rates and the effect of gravity on these particle clustering. So the main effect of gravity is that it suppresses the clustering between same-sized droplets. At the same time, for droplets of different sizes, the scales at which the transition from a power law to plate 2 for the RDFs is much larger for sedimenting droplets. So in terms of the collision kernel, for equal-sized droplets, sedimentation reduces the chances of collision. And for unequal-sized droplets, sedimentation enhances the collision kernel. That's it. Yeah. Thank you.
Thank you very much, Vishnu, for your presentation. Well, you remove your slides very quickly.
Oh, sorry.
No,
I didn't see what I was doing, so yeah.
Once again, use the chat, and we have a couple of minutes. I had two questions. The first one is a numerical one. You didn't have any issues with the load balancing in your simulations?
No. So 62 million particles with, I can't really remember how many cores I used. I think it's 4,000 cores. But yes, it was fine for me. We didn't have any issues with load balancing for this simulation.
Well, it's good to hear.
Yeah.
And I'm still trying to process why gravity is suppressing clustering.
Oh, I didn't mention that. So the main reason is that particles, so there's reduced interaction time between the particles and an eddy, because they tend to, because of the effect of gravity, they tend to cross the eddy much faster, which means that they're much likely to kind of be pushed away. Gravity takes them away much faster. It is the time it takes for a particle to cross an eddy. It's much faster when you have the influence of gravity. Sorry, that's the main thing I should have mentioned.
Okay, I will have to think about that. Good. Thank you very much. And once again, if you have any questions, please feel free to use the chat. So thank you again, Vishnu, for your nice presentation. Right, our last presentation is from Anton from the University of Liverpool. So Anton, yes, we can see a nice June, and now we can see your slides. We can hear you as well. So for the last presentation today, we are going to move to linear modal instabilities for wings at low Reynolds number. And this is a presentation from the group of Vassilios Theophilis at the University of Liverpool. So please, Anton, you have 15 minutes for your presentation.
Yes, thank you for the introduction. My name is Anton. I'm working with Vassilios Theophilis and also Wei He at Liverpool. And I'll talk about modal instabilities around swept wings. This presentation covers the stability analysis side of a larger project that includes also our colleagues doing computational work at UCLA, as well as experiments at RPI. And we are funded by the Air Force Office of Scientific Research. I will start with some brief discussion of background and theory, and then move on to numerical methods, mention the computational cost of the simulations, and then finish off with model results. Now, our work builds upon the previous efforts of Tyra and Kalonius, the global stability analysis of He et al., who considered both span-wise periodic as well as three-dimensional elliptic wings, and especially the recent publication with our colleagues from UCLA on swept and unswept wings. Their recent findings unraveling complex vortex dynamics over these geometries set the scene for what we do here. And our analysis is at similar conditions of laminar, incompressible, massively separated low Reynolds number flow over finite wings, with the domain covering half wing body as shown here. And we are specifically interested in the effects of wing geometry on the modes. So linear stability theory decomposes the flow onto a base flow Q bar and a small perturbation Q tilde. And the base flow is laminar, steady or unsteady, depending on the geometry and Reynolds number. And by methodology, we can divide the analysis into operator or data-driven. Operator-driven approaches involve linearizing the equations of motion and then choosing a suitable model ansatz for the perturbation. In this case, both the base flow and the perturbation are three-dimensional, so we use what's known as the triglobal approach, which, when substituted into the equations, results in a matrix eigenvalue problem where the operator A reflects the discretization of the equations. In data-driven approaches, on the other hand, a set of flow snapshots is collected into a data matrix X with no knowledge of the governing equations necessary. And we use proper orthogonal decomposition, which determines the optimal set of orthogonal modes to represent the flow in terms of energy, and dynamic mode decomposition, which gives modes of a single characteristic frequency resulting from the eigen decomposition of the best fit linear operator. DMD can also be considered the numerical approximation of Koopman modes. And both methods lead to an eigenvalue problem, which is solved to obtain the modes. All the analysis and all the results I show here is for a fixed Reynolds number of 400 based on the chord. Now, the angle of attack, alpha, the angle of sweep, lambda, are defined as follows, with the symmetric aspect ratio, SAR, defined based on the half span from symmetry to the tip. We use spectral element codes to compute both the base flow, and for the modal analysis, if we consider a signal from a probe, in the linear global modes are associated with the linear growth stage, and we compute them with time stepping in Nectar++, and more recently we started using also NEC 5000. We use selective frequency damping to obtain artificially stationary but linearly unstable base flows, and these computations were done on Archer. For the data-driven analysis, we carry it out in the nonlinear saturated regime, where we use POD and DMD to explore a larger parameter space and obtain the most energetic structures, whereas the more expensive tri-global methods are reserved for a smaller number of conditions of interest. So I want to briefly mention the high computational cost of this work. The cost of data-driven analysis is pretty much negligible. Some of it could probably be done on a laptop, but the main cost comes from global stability analysis. So to compute a typical Archer job would be 960 cores, and either 24 or 48 hours. 2 or 3 such jobs would be needed to compute the flow, and then 5 or 6 to perform the selective frequency damping. And in the end, the time stepping itself to obtain the eigenmodes would be about 2 more jobs. So this amounts to about 5,000 kilo allocation units per stability analysis case. So this work would really be impossible without using Archer. Now we look at some of the results, and specifically first we look at the base flows themselves, starting with the effects of angle of attack. So here we have alpha increasing from 14 to 22 degrees. At about 14 degrees, the flow becomes unstable with periodic shedding and the symmetry plane. With increased alpha, the wake becomes more complex, and eventually 3 regions can be seen behind the wing, which are the wake, close to the symmetry plane, a stable tip vortex, and an interaction region between the two that consists of braid-like vertical structures. And the formation and dynamics of these structures were discussed in more details in the recent paper with our colleagues from UCLA. Now we fix angle of attack at 22 degrees and instead change sweep, and also look at the shorter wing shown on the right here with an aspect ratio of 2 rather than 4. And with increased sweep, we see these interaction region structures moving towards the tip. Eventually at 15 degrees, the vortices behind the wing no longer pass through the symmetry plane. And at sweep of 25 degrees, there is the separation bubble on the wing splits into 2 parts, and in the middle there is a region of steady attached flow. Effects of sweep are similar for the shorter wing, with the exception of due to the stronger wingtip effects, there is no true wake region behind the short wing. So now we look at the global modes, and the graph here shows amplification rate and frequency in terms of non-dimensional Struchel number. And I show here leading eigenvalues of different conditions as shown in the legend plotted together. So for the unswept case, the leading unstable mode takes the form of wake instability at the symmetry plane. So I show here contours of Q criterion of the mode, and this is top view symmetry plane here, and the tip is here. For the shorter aspect ratio 2 wing, the mode is qualitatively similar but more amplified, and for a sweep angle of 5 and 10 degrees, the structure moved towards the tip, but qualitatively they are still reminiscent of the same mode on the unswept wing. We refer to this as the wake mode. Now at the sweep of 15 degrees, the different, less amplified vertical mode is dominant. And finally, at sweep of 30 degrees, the leading eigenmode is damped. It takes the form of a tip instability peaking further downstream behind the wing. So to verify our results, we have used also the other spectral code NEC 5000 to compute the modes. And here I show a comparison of the leading modes, the spectra for arbitrary swept case of 5 degrees. And we see very good agreement in terms of frequency between the two codes. Now the amplification rate of the leading mode is a little bit different. We attribute the difference to the different levels to which the selective frequency damping was converged between the two codes. And if we look at the eigenvector in terms of v velocity, we see very good agreement between two codes. Now, looking in more detail on the velocity components of the wake mode, of the wake global mode, different sweep angles, and with the shorter wing, again, we see qualitative similarities. Overall, the mode is less amplified with increasing sweep and more amplified at the shorter aspect ratio. And overall, the structures seem to be very similar between the two aspect ratios. Another test we carry out is to take the global mode and impose it on top of the steady base flow at a very small amplitude and let it grow. So this is the black curve here on the left. And as expected, we see a region of linear growth and eventual saturation and nonlinear behavior. And we impose on top of this the red curve, which is just the DNS used to obtain the mode in the first place. And the simulation initialized from the global mode takes much longer to reach this state. So the red curve is shifted to the right just to try and match the peaks. But overall, we see that the growth of a single global mode captures quite well overall the behavior of the flow. And further, if we look at the flow field at the beginning of the nonlinear saturated regime at about here in terms of time, we see good qualitative agreement. This is slightly out of phase, but overall, we can see that the growth of the most amplified unstable mode leads to the wake structures observed in the flow. So far we have been looking at the global modes associated with the linear regime. Now we will take a look at pod and DMD results where the data was taken well into the nonlinear regime. So again, we first look at effects of angle of attack. This is the base flow, just as a reminder. And I should mention that we do both pod and DMD, but for this periodic flow, they're in very good agreement. So they effectively deliver nearly identical results. And there are two dominant most energetic modes that we see. One is the interaction region mode, sorry, the interaction mode, which takes the form of structures behind the wing here, vertical structures that at higher angles of attack reflect the curvature of the vortices being shed from the wing. They also have these structures that reflect the braid-like vortices in the base flow. The wake mode, on the other hand, at a different frequency, has structures mostly parallel to the wing and centered closer to the symmetry plane. And now again, we fix angle of attack at 22 degrees and increase sweep. And we see those two modes up to a sweep of 15 degrees. At 15 degrees, the wake mode is no longer present, and the spectrum is dominated by higher harmonics of the interaction region of the interaction mode. Sorry. And eventually at close to 30 degrees of sweep, there is another mode comprising of streamwise elongated structures that gains energy in the POD spectrum, and it is the most energetic at sweep of 30 degrees. Now, lastly, if we fix the sweep at 30 degrees and look at the shorter aspect ratio to wings, so these two modes are the same as on the previous slide, we see a similar streamwise mode on the shorter wing. However, it's not the most energetic one. Instead, a tip-like disturbance is the most energetic. So again, this reflects the fact that even at high angle of sweep, the short wing is dominated by tip effects, whereas span-wise flow effects take precedence over the longer wing at aspect ratio 4. So to conclude, we have looked into the effects of wing geometry on linear model instabilities. Overall, the increase of sweep has a stabilizing effect on the flow, while of course increasing angle of attack makes the flow more unstable. Global modes computed for this three-dimensional geometry for the first time were shown, and we have seen their evolution with wing sweep. It was shown that the unstable mode leads to vertical structures that are observed in the flow. And also data-driven model analysis revealed several energetic structures in the wake, including the interaction mode. And those effects were also observed at different geometrical conditions. Now, we hope that documenting these instabilities at low Reynolds number may reveal mechanisms that are relevant for more realistic flight conditions. And in terms of future work, we are expanding our analysis to look into tapered wing, where the effects of taper seem to have quite substantial effects on the flow. And we also intend to conduct a joint stability analysis to be able to identify most sensitive areas in the flow, for example, for forcing. Now, this concludes my presentation. We thank UKTC for computational resources, and thank you for your attention.
Thank you very much, Anton, for a nice presentation. We have a few minutes, so if you have any question, please feel free to speak now. And while you are thinking of questions, I had one question about, because you show some three global mode at very, very low strual, but then later on in your presentation, you showed that they correspond to elongated streamwise structure. So that was one question that I had. The other one was, so you have in some setup, you have an interaction mode and a wake mode, and how are they competing with each other? And is there one that is more dominant than the other, or?
Right. So yeah, with the elongated structures, I believe you refer to the model data-driven results to the pod and DMD mode, right?
Yeah.
That were at very low Struhal. Yeah. So we didn't see those structures in the global analysis, in the tri-global analysis. But then again, with time stepping, we can't really converge a lot of modes, typically probably less than 10, usually of the most dominant.
Yeah.
So they might exist. And secondly, we basically conducted the data-driven analysis in the nonlinear wake. So we could have done it in the linear regime, and we probably would get very similar results to tri-global. But instead, we just wanted to document the most energetic structures for a wider range of conditions. Now, in terms of the second question, so the wake mode versus the interaction mode is more energetic if we look at the pod spectrum for most of the conditions. Actually, for all of the swept cases, the wake mode is usually the second most energetic pod mode. And that pretty much remains so until the emergence of these various low frequency streamwise modes at very high angles of sweep.
Very good. Well, thank you very much, Anton, for your presentation, and thank you very much again for all the speakers today. That was a very nice session. We are going to have one more online talk series in July before taking a break in August. And then we will, of course, depending on the COVID-19 situation, we'll reassess the situation to see if we carry on with those online talks or if we organize an in-person meeting. So we will keep you updated over the summer. And for the last, in July, the last talks, I will also give you an update around Archer 2. I'm hoping that we will have some more definitive news around Archer 2. I had a meeting with the PSRC yesterday, and the latest plan is that the 4 cabinet will go down possibly in June, so not in May anymore. And hopefully the full Archer 2 should start to be available in July, maybe in August. So it's still a bit blurry, but hopefully I will be able to give you a proper update early July. And it's a bit, there's a lot of uncertainties, but hopefully we'll have more clarity in a few weeks' time. Sorry, I'm talking about July. It's early June. The next series of talk will be early June. So I will give you an update on Archer 2. So we will only have 3 talks and 1 update from me about Archer 2. So thank you very much, everyone, for attending. Everything is recorded, so we'll put everything online, and hopefully we will see you soon for the June talks. So thank you very much all, and have a lovely weekend.
Thank you, Ziva. Bye.